today we'll talk about chapter 11, the geometry nonlinear analysis. So for this chapter, we will cover the following four contents. So first is the geometry nonlinear problems. Second, we will go through the FE formulations of the geometry nonlinear problems. Third is the FE equations of the geometry nonlinear problems. And fourth is the constitutive equations of geometry nonlinear problems. So part 1 is the geometry nonlinear problems. First is the definition of the geometry nonlinear problems. So what are the geometry nonlinear problems? It means large displacement, large rotation, and small strain. This is the first case. So the first case, we have large displacement, we have large rotation, but we have small strain. And the second case is the large displacement, large rotation, and also large strain. Okay. And the FE analysis of geometry nonlinear problems. So we will talk about the strain and stress description, and we will talk about the FE formulation of geometry nonlinear problems, and also we'll talk about the constitutive relation of large deformation problems. So here is the definition of geometry nonlinear problems. We said we have two scenarios, and the first scenario is the large displacement, large rotation, and a small strain. Okay, and a small strain. So we have we use a figure to illustrate this. So we have a deformable body here, and then after the deformation, it will displace to this location. We can say from this location to this location, it has gone through large displacement, large rotation, but the deformation is small, so there's a small strain. And in this condition, all the theory we have for the small deformation theory cannot be applied to this scenario. So therefore, we have to consider the geometry nonlinear problems, and we have to consider different formulations, and we have to use different theories to solve these problems. Okay. We see here the linear theory cannot be applied. So in the previous chapter, we all assume, for example, the geometry equation and the constitutive equation based on the linear theory. But here we cannot apply those theory, and we have to change it. We have to use different theory. Okay. And the second scenario is the large displacement, large rotation, and large strain. Okay, so as shown in this figure, so this is the deformable body before the deformation, and then this is the deformable body after the deformation, and we can see it has gone through the large displacement, large rotation, also very large strain. We can see it's changed a lot. Okay, and for this case, this is also a very typical geometry nonlinear problems. And we said for the geometry nonlinear problems, we have to use the new theory. We have to use the new equations and formulations to solve it. And here, and also for the strain, we have to define new concept or new strain variables to describe the large deformation or the geometry non. We introduce to you how we get those new definitions, how we get those new variables. So to describe the geometry nonlinear problems, so we have to use the configuration. Okay, we have to use the configuration. Configuration is the states of the deformed body at different time points. So for example, here we say the initial configuration is the deformed body at time 0. Okay, that's it, before the deformation. And the current configuration is always means the deformed body at time t. And the next configuration means the deformed body at time t plus t. Okay, so we have the p and the 0, we have the p t and the p t plus t. Okay, this is the initial configuration. This is the current configuration, and this is the next configuration. And this is the corresponding deformed body. So this is the deformed body at time 0. This is the deformed body at the current time point. This is the deformed body at the next time point. Therefore, you can notice for all those variables, for the geometry nonlinear problems, we have another superscript. So we have another superscript to indicate which configuration the variable is defined in. Okay, so for example, we have the st. Here the t means this variable is defined in the current configuration or in at time t. And if we say here the v t plus t means the volume of the deformed body at time t plus t at the next configuration. Okay, so clear for this. So and we can also say the main difference. Okay, so let's have a look at the slide. So we have the coordinates of p. Okay, we have the coordinates of p, and then this is the coordinate. This is the coordinate of p points, and then they have the x coordinate of xi 0, and we have q, another point. Q is we describe using the initial configuration. So we have xi 0, dxi 0, and then after large deformation, they move to another location. So xit plus dxit. Okay, and this we are using the current configuration to describe the points. Okay, and so we can say, and the distance between p and q here is in the initial configuration is dxi 0, and here the distance is dxit. Okay, right. So here the distance is dxit plus delta t. So we can say the distance between the 2 points is also changing, and we are describe the distance using the variables in different configuration. Okay, so this is the way how we describe the geometry nonlinear problems. And then we come to the string description. So the change of point location from the initial configuration, that is the time 0 configuration, to the current configuration, that's the time t configuration, can be seen as a mathematical transformation. So the change of the point location, we can say from the mathematical point of view, it's just a transformation. So here you say we have the variables in the initial configuration, and then we have the variable in the current configuration. So there's a kind of mapping or the mathematical relationship between them. And because of the one-to-one mapping, so we know it's the same deformable body. So of course there's a one-to-one mapping. Because you are not able to add more point or remove any point from the deformable body. It's still the same deformable body. Therefore, there's a one-to-one mapping of the point. Therefore, the inverse transformation also holds. Therefore, we can also use the current configuration variables to calculate the initial configuration variables. So this is we have this in our mind. So we have this mathematics in our mind. Then we can divide the string description in different systems. Okay, so first we describe the string in the Lagrange coordinates. And here is the definition for the Lagrange coordinate. So what is Lagrange coordinate? It takes the coordinate at the initial configuration. Okay, this is important. They take the coordinates at the initial configuration as the unknowns to describe the variable, and they use the initial configuration to describe the deformable, or to describe the deformed configuration, which we see here. So this is in the Lagrange coordinates. So we say the variables, the unknown variables are the variable in the initial configuration, because we say that all of them are 0, so they are, and then we use it to describe the variable in the current configuration. Therefore, it's using the Lagrange coordinates, using the Lagrange. Or coordinate, or in comparison, we have the Euler coordinates. What are the Euler coordinates? So the Euler coordinate, they take the coordinates at the deformed configuration as unknowns to describe the variable, and use the deformed configuration to describe the initial configuration. So it's inverse. So they use the variable or coordinates in the current configuration to describe the variable in the initial configuration. So if it's doing this, then we say it's the Euler coordinate, or is using the Euler coordinates. It's the Euler is described in the Euler system. Okay. And so then let's have a look how we divide the string, how we work out the formula or the expression for the string in different coordinates or in different systems. So first, in the Lagrange coordinate, we already know in the Lagrange coordinate we using the those unknown variable in the initial configuration as the unknowns, and we use those to describe the variable in the current configuration. Okay, then our string, this is the, then we can write out the dxit. What is dxit? We should come to here. This is the dxit. That's the distance between P and Q in the current configuration. Okay. So this is PQ, the distance of PQ in the current configuration, and dxj. dxj, what's dxj? We can say dxj. We can say we are using j because we want to make a difference to the I. So this is PQ in the initial configuration. Okay, so we can do the mathematics here. Then we get this. So then we introduce a new symbol. This is our new symbol. It's just it's similar to the index notation. So we want to simplify the writing of those. We want to simplify the writing of those. Therefore, people introduce this new symbol or new rules to replace this one. So let's have a look. So this t, it means it's the one in the numerator, and this 0 means the one refer to the one in the denominator, and this comma means we take the partial derivative. Therefore, this one means this equals to partial x. The first I is the one appear in the numerator. So, and we say this one, the superscript, is the one appear in the numerator. Okay, and then this one, the subscript is the one appear in the denominator, and the comma, after the comma, the index appear in the denominator. Therefore, we say this one is is actually this one. Okay, but if we write in this form, it's much easier and much simpler. And then accordingly, we can have the definition in the Euler coordinates. We can have the definition in the Euler coordinates. And in the Euler coordinates, we use the variable in the current configuration as the unknowns, and we use it to describe the variable in the initial configuration. And therefore, accordingly, based on the mathematical, we can have this formula. Again, we have this one. We have this symbol. Okay. Then we want to, in order to work out the string. Okay, the string, from the previous lecture, we know the string. The string is the change of the length. Okay, is the change of the length divided by the initial length. Therefore, we have to work out the change of the distance, the distance between P and Q. If we work out the distance in the initial configuration and in the current configuration, then we can work out, based on the concept of the string, we can work out the string. Okay, so let's work out the distance. Because it's a distance, therefore we have using the square. So ds0, which means it's the this is the ds square, so which is dxi0 we times dxi0. We said dxi0, this one is the distance between P and Q in the initial configuration. But there's a symbol here, which means there can be positive and negative. Therefore, we take the operation of square. Okay, and then by using this formula, then we can get this one. Okay, similarly, we can work out the distance between P and Q at the current configuration. So, and then we take this formula into the formula. Then we get the distance in the current configuration. Okay, that's it. It should be easy to understand. And then we want to work out the change of the line, or the change of the distance. The change of the distance can be expressed as this. This is the change. Okay, the change of distance, and it can be expressed in two ways. So first is using, let's have a look. So this is using the x0. Okay, this is using xt. So this is in the Lagrange coordinates. This is in the Euler coordinates. Okay, this is in the Euler coordinates. And then from here we know this is the string. Okay, so then we can have the definition of the string in two systems. Okay, in two systems, and this is the Lagrange. This is using the variable. Then we have different. So we should have different. So we have this is Lagrange, and this is the Euler, and then but we cannot say, okay, this is the string in the Lagrange coordinate, this is the string in the Euler coordinates. So we have to give them the new name in order to refer to them. So under the string in the Lagrange coordinate, we call it the green string tensor. So this is a very important concept. So whenever you heard about the green string tensor, you should have this formula in your mind, and you should know this is defined in the Lagrange coordinate. So which means we use which means in this formula, the variable, like here, like these are the unknowns. Those are the unknown variables. Okay, and in comparison, we have the string in the Euler coordinate system. Okay, and this is called Amansi string tensor. Okay, and in this formula you have the x, I, t. These are the unknowns. So these are the unknown variables, because we said in the Euler coordinate we have we are using the variable in the current configuration as the unknown variables, and the variable in the initial configuration can be expressed using the variable in the current configuration. Okay, so this is the concept you should have in your mind, and you should have in your mind forever. So we have for the geometry nonlinear problems, because we have two coordinate system. We have the Lagrange coordinate system, we have the Euler coordinate system. Therefore, the string, we have two kind of string. We have two types of string. So firstly is the green Lagrange string tensor, or sometimes we say green string tensor, and this is the string defined in the Lagrange coordinates. And we have the Armancy string tensor, and this is the string defined in the Euler coordinates. And there's a relationship between these two string tensor. Okay, so from mathematical point of view, we can easily get the relationship between these two string tensor. Then, so here we have our string description in the geometry nonlinear problems. Then let's have a look at the string displacement relationship. The string displacement relationship for the geometry nonlinear problems. Okay, so the displacement of a point from time 0, or the initial configuration, to time t, as to the current configuration, we can express as this. Okay, so this is the point at the current configuration, and this is at the initial configuration. So we can describe the displacements, and then we can have this. So if we take the partial derivative, okay, if we take the partial derivative, this equals to partial derivative u I t and the partial u j 0. All right. So this equals to this, and this one equals to partial x I t partial x j 0. Okay, so right, and then this one is delta. Okay, and then this one is delta, which means we first do x I t equal to x I 0 plus u I t, and then we take the partial derivative to this equation, and we get this one. Okay. And we know there's a relationship between the coordinates at the Lagrange and the variable in the Euler coordinate system. So we can also have this formula. Okay, we can also have this formula. And for this formula, we first do x I 0 equal to what? This one equal to x I t minus u I t, and then we take the partial derivative x I 0. We take partial derivative to x j t. Okay, and then equals to, and this one becomes to delta I j, and then this one equals to u I j t t. Okay, t. Let's see. So this is for the mathematics. And then we have the green string tensor, Armancy string tensor. This we already mentioned. Okay, we already introduced this formula. And then we replace those coordinates. We replace those coordinates using those formula, and then we have the relationship between the string and the displacement. You see, these are the displacements, and we have the relationship between the string and the displacement Therefore, those are the string displacement relationship for the geometry nonlinear problems. Okay, so by this way, we have worked out the string displacement relationship for the geometry nonlinear problems, and we can see they are different with the linear case. But if you consider, or if you reduce this to small deformation case, you can see so the second order can be ignored, and then those formula, they are reduced to the linear elastic small deformation formula. Okay. Then let's introduce another very, very important concept, the deformation gradient. The deformation gradient is the vector difference between P and Q. So we have the P and Q, and it's the vector difference. So therefore, let's have a look at the vector first in the current configuration, then in the second configuration. So in the current configuration, we say from P and Q, we describe it as dxt. In the initial configuration, it's dxi0. Okay, and then these are based on the. So this is the mathematic. Okay, this is the mathematic. We can express it like this, and then we introduce this symbol, and then we express it like this. So this is the mathematic. So we said that we define the deformation gradient as the vector difference between these two, between the P and the Q. Therefore, we defined it as this. Okay, we defined it as this, and then from the mathematical point of view, it equals to this. So this is our deformation gradient. Okay, this is our deformation gradient, and we can also express in the initial configuration. Okay, this is present in the current configuration. Okay, so this is the definition. The definition for the deformation gradient. So let's have a look. How do we work out the deformation gradient? We use an example to demonstrate how can we work out the deformation gradient. So the relationship between the nodal coordinates at the time are known. So for this one, we have it's a triangular. We have 1, 2, and 3, and this is at 0 times 0, or the initial configuration, and this is at time t. So this is the current configuration. So it's a move to this one. We can see what it's doing. It's doing a rotation, right? You see, it's doing a rotation. So therefore, we say the point 2 they moved upwards, and point 3 they moved anti-clockwise. Okay, so at the we define those variables. So we define the coordinates at time t, 0, coordinates x2 and y2 at time t was this function. Okay, we defined the coordinates for point 3 was this function, and by using all those information, we want to work out the deformation gradient for this deformable body. And let's have a look at the procedure. Okay. So at time t, the coordinates of any point within the element, we can write out those. Okay, this is based on the interpolation, the idea of the interpolation. So we have the coordinates at the 3 points. These are the 3 points, and then this is c1, c2, c3. They are our interpolation function. So based on the interpolation, the idea of interpolation, we can work out the coordinate of any point within the element. Then we can work out, okay, at time 0. So at the initial configuration, we just here we set t equals to 0. Then we can have the configuration or the coordinates at the initial configuration. Similarly, for the y coordinate, If we set t equal to 0, then we have the coordinate at time 0. And then because x10 equals to x30, okay, x30, because at time 0 we say the coordinate, this is our x, this is our y. So at this initial configuration we can notice the x coordinate of 1 and 3 they equal, and the y coordinate of 1 and 2 they equal. Okay, all right. So and at this initial configuration we also notice for point 2 at the initial configuration the coordinate is 2, and for point 3 the y coordinate is 1. So all we know all this information from the figure, and then we can work out. So by using those equations we can work out the parameter, can work out the coefficient. So we can work out the coefficient for C2 and C3, and then we can express those equations. So after we work out, then we can rewrite those equations. Okay, we rewrite the x and the t, and then we can, based on this, so we take the partial derivative. So we take the partial derivative to the corresponding variable. Then we can work out this variable. Okay, so this is the mathematical part of it, and this variable is our deformation gradient. So by this approach we have worked out the deformation gradients. So second example, let's have a look how we work out various string for the one-dimensional problems. So we have up to now we have introduced the string defined for the small deformation case, and the two string defined in the large deformation case, or the geometry nonlinear problem case. So here we have a look how we calculate the different strings. So we have a 1D problems here, and this is the initial. Okay, this is the initial state. This is 0, and this is t. Okay, the initial length is L, and the current length is small l. Okay, so we have the displacement expressed in this term. The displacement. So this is xt, and this is x0. Okay, x0. Therefore, the displacement can be expressed in this term. Okay, and in this term, and we want to work out different string. First is the engineer string. We say engineer string is most used in a small deformation case, and is the change in length divided by the initial length. Okay, we can say because it's a small deformation case, therefore we don't have the higher order term. But these two strings are defined for the geometry nonlinear problems. Therefore we have the higher order term. We have the higher order term to more accurately describe the problems. So we have the green string. Beside the green string is defined in the Lagrange coordinate. And we have Ramansky string. This is defined in the Euler coordinate system. So, and then by using this equation, we can work out the green string and the Ramansky string. So by the green string, we take the partial derivative to x0. This is our unknown variable, because this is our unknown variable. And for the Ramansky string, our unknown variable is xt. Therefore, we take partial derivative to xt. So we take partial derivative by xt, and then we put this formula into those equation. Then we can work out this is the green string. This is the Ramansky string. Okay, so we have different string. This is a very important concept. So you cannot use the engineer string for for the large deformation case or for the geometry nonlinear case, if you use this, it's wrong, absolutely wrong. You have to change to different. You have to use different string for different scenario. So let's have a look. We give a plot. Okay, from the previous slide, we have calculated the formulation for the engineer string, the formulation for the Greenskin string, and the formulation for the Amasa string, and we plot it here. So we have the x coordinate is initial length it's deformed length divided by initial length, and when it is 0, which means they have no deformation. When it is bigger than when it is 1.0, then there's no deformation. When it is bigger than 1.0, then it is lengthened, so it's become longer. And when it is smaller than 1.0, then it's shortening. It's become shorter. Okay. And then here in the y-axis we have the string. Okay. So when there's no deformation, when the length do not change, then there's no string, so there's 0. Okay. When it becomes longer, so we have the positive string. When it becomes shorter, we have negative string. So this is clear. And we say when there's a small deformation, in which case the small deformation, so the string is small. When there's, we say that we regard this as small deformation. And in a small deformation case, we can say the values for the 3 string, they are identical. But when the deformation becomes large, and we have geometry nonlinear problems, then there's a gap. There's a gap between different string. We say there's a gap between different string. Therefore, in the geometry nonlinear problems or in the large deformation case, we have to be careful. We have to choose the approximate or appropriate string to describe our problems. Okay, so it's very important you have this figure in your mind forever. So don't make mistake, don't make error when you choose which string to describe your problems. Okay, we have talked about the string description. We have said for the geometry nonlinear problems we have different string, and we should use the approximate one for different case scenarios. Now we talk about the stress description for the geometry nonlinear problems. So here is the definition for the stress. So we have also we look at the figure. So the figure we have the Lagrange coordinates, also the Euler coordinates. So we have x0, xt, and this is in the Lagrange coordinate. This is in the Euler coordinates. Okay, and we have for the geometry nonlinear problem, we have the Cauchy stress. We call it the true stress. Cauchy stress is the force in the unit area in the deformed configuration. So this is similar as the true string. So that for the true string, we divide in the deformed configuration. And we have the engineer stress. So we use the force in the unit area in the initial configuration. So corresponding, we have the engineer string. So engineer string is the change in the length divided by the initial length. Okay, divided by the initial length. Okay, and let's have a look at the stress. Before the deformation, the stress is the force divided by the initial area, right? And after deformation, the stress is the force divided by the deformed or the area in the current configuration. Okay. And there's a relationship between the surface force between before and after deformation. This should be easy to understand. So then we have the Lagrange definition. the Lagrange definition, the force component equal before and after the deformation. So if we use the Lagrange deformation, which means the force component, the surface force, this is before the deformation, that's the initial configuration, and this after deformation, that's the current configuration. They equal, we make them equal to each other. And we have the Kirchhoff definition. The Kirchhoff definition, okay, so by the figure, so it comes corresponding to this figure. So this is, we have the initial configuration, we have the current configuration. So the surface force, they equal to each other in the two configurations. This is the Lagrange definition. But in the Kirchhoff definition, there's a transformation between the forces. So we have the force in the initial configuration. We have the force in the current configuration. They don't equal. We say they don't equal to each other. So there's a transformation. There's a transformation between them. So we have the transformation described. The transformation function described as this. Okay. So this is the definition because we want to describe different scenarios. I think here there'll be a mistake here. It should be, sorry, this is right. So this is the definition of this variable. Definition of this variable. Then we have the stress definition. The stress definition, we have the following relationship holds. So we have the this one, and here n is the cosine of the normal of the surface, and the tau is the Cauchy stress tensor. It's the stress component in the deformed configuration. That's the stress component in the deformed configuration. So we have the relationship of the following relationship. And first we use the Kirchhoff regulation. Use the Kirchhoff regulation, which means we use we use this assumption, which means the force, they don't equal to each other. And under use the Kirchhoff definition, then we can express the force, and then we have this one is the Kirchhoff stress, and we call it the second polar Kirchhoff stress. Okay, and also we call it Kirchhoff stress tensor, or we call it nominal stress because it use the surface area in the current configuration. Okay. And then we have we use the Lagrange regulation. Using the Lagrange regulation, then this is the surface. This is the surface force in the initial configuration. This is the surface force in the current configuration. Then we can obtain another variable, and we call this variable as the first polar Kirchhoff stress. We call it Lagrange stress, because we are using Lagrange regulation. And here the superscript means the stress in the deformed configuration. So this is in the deformed configuration. And the subscript means the stress is measured in the initial configuration. So which means the stress is measured in the initial configuration. Okay, so for the stress, here we have introduced two very important concepts. You will meet this concept very often in your future study or engineering problems. So I have the second polar Kirchhoff stress, also called Kirchhoff stress or nominal stress, and we have the first polar Cauchy stress or the Lagrange stress, and you should be very clear how they are obtained and what's the difference between those different stress. And we should know those are the stress for the geometry nonlinear problems. So it's for the large deformation case. And from the mathematical point of view, we can also know there's a relationship between different stress. Okay, so according to the mass conversion, and we have those, so which means the mass, they don't disappear. So we have this mathematical formulation, and then we can obtain the relationship between the Cauchy stress and the forced Cauchy-Hopf stress. Okay, this is the relationship between this is the Cauchy stress, right? This is the forced Cauchy-Hopf stress, and also we can obtain the relationship between the Cauchy stress and the second Cauchy-Hopf stress. So this is the Cauchy stress, and this is the second Cauchy-Hopf stress. And also we obtained, from mathematical point of view, we can obtain the relationship between the first Cauchy-Hopf stress and the second Cauchy-Hopf stress. So for the geometry nonlinear problems, we also will, similar to the string, we also obtained three variables: the Cauchy stress, the first Cauchy-Hopf stress, and the second Cauchy-Hopf stress. We also obtained three variables, and there's a relationship between different variables. So let's have a look, an example to demonstrate how do we calculate different stress for the geometry nonlinear problems. So we have a deformable body here, and what it's doing, I think it's doing the rotation. Okay, it's doing the rotation. So let's have a look. The deformable, we use the deformable gradient to describe the deformation, and we gave the initial Cauchy stress, is the initial Cauchy stress, and we have the deformable deformation gradient, and we want to work out other stress components like the first Cauchy-Hopf stress, second Cauchy-Hopf stress. Okay, so we set the time t, because this is a deformation gradient, is a function of t, and we set time t as this. Okay, then we get the formulation for the deformation gradient, the Jacobi of the Cauchy-Hopf of the deformation gradient equals to 1, and then we have our Cauchy stress equal to this. And then based on the relationship between Cauchy stress and the first polar Cauchy-Hopf stress, we can work out from the mathematical point of view, we can work out the first Cauchy-Hopf stress. Similarly, we can work out the second Cauchy-Hopf stress. Okay, so there's nothing we want to go too much detail, because this is only the mathematics here. And then the second example is to link the various stress for the uniaxial tension problems. So we have a uniaxial tension. For the uniaxial tension, we want to work out the various stress, and this is uniaxial. And because it's uniaxial tension problems, therefore we have this relationship. Okay, we have this relationship. Okay, and this is the deformed length, is the initial length, and this is the deformed dimension in the y direction. This is the initial dimension in the y direction, and this is the deformed dimension in the z direction, and this is the initial dimension this is the length in the initial length. Then we work out the deformation gradient. So we said deformation gradient is very important for the geometry nonlinear problems. So because all other variables are worked out from the deformation gradient. So by using the equations, we can work out the deformation gradient for these problems, and then we can continue our calculation to work out other variables. So first is the Cauchy stress. Second is the first Cauchy-Hopf stress. Third is the second Cauchy-Hopf stress. So once we work out the Cauchy stress, then we can use the relationship to work out the first Cauchy-Hopf stress and the second Cauchy-Hopf stress. So this is also the mathematics. So we don't repeat it here. So you should do your practice to work by hand by yourself and to see whether you can get those or not. Okay. So then part 2 is FE formulations of the geometry nonlinear problems. And for this part, we are going to quickly go through. We don't go too much details here. So for the FE formulations, so similar as the previous problems, we use the virtual displacement principle. We use the virtual displacement principle. But the difference is we use the variables in different configurations to represent the quantities and to represent points. So we have those 3 variables, and this is referred to the coordinates at time 0, and this is referred to the coordinates at time t. This referred to the coordinates at time t plus delta t. Okay, and then u is the point displacement referred to time t. This is referred to time t plus delta t, and then we have the relationship between each other. Okay, and then the displacement increment we can written as this. So it's the difference between the displacement at t plus delta t minus the displacement at t. Okay. Then we can write out the virtual displacement principle at t plus delta t. So for the geometry nonlinear problems, you have to mention which time point you are working at. So this is important here because we are working at t plus delta t. So we have all those variables expressed in t plus delta t. So here the tau is the Cauchy stress at t plus delta t configuration. Okay, then we have the strain, then we have the virtual work at the t plus delta t. Okay, and here this is the body force, and this is the surface force at t plus delta t configuration, and they are measured at the same configuration. So they are measured maybe at the current configuration. Okay. Then we have the virtual displacement principle expressed as this. So it's very similar to our previous equation, but the only difference we have put the configuration into those formula. Okay, because the variable at t plus delta t configuration are unknowns, we use those as the unknown. The above equation cannot be solved, so we need to refer to one knowing variables or knowing configuration, and then therefore the following 2 methods are proposed. So depends on we take which configuration as the knowing configuration. So we have different method. First is the total Lagrange format. The total Lagrange format, the word variable using the initial configuration as the reference configuration. And then we have the update Lagrange format. In the update Lagrange format, all the variable use the deformed configuration. That's the configuration at t as the reference configuration, and therefore the configuration keeps changing in the solving process. Okay. And first is the total Lagrange format. So the corresponding virtual work principle, the deformed configuration is transformed into the initial configuration, because we are for the total Lagrange format we use the initial configuration. Therefore we change to the initial configuration. Therefore you see those are the 0, those are 0. These are the initial configuration. These are we change them to the transform them to the initial configuration. We mentioned we have the 1-to-1 mapping. Therefore we can easily make the transformation. And the transformation process is as below. So we have the surface and body force equations, and we have the mass principles. So those are the we will take use of those equations to do the transformation. Okay, those are the many mathematics involved. Then we have the variation of the string. Okay, and also for the string we use the total Lagrange format. Therefore we have the Kirchhoff stress and the green string tensor at the t plus delta t configuration. We use the initial configuration as the reference. Okay, and then the virtual displacement principle based on the initial configuration can be written as this. Okay, we use the initial configuration we see here. We use those as the reference. So this is the total Lagrange format. Then we have the updated Lagrange format. So in the updated Lagrange format, the corresponding virtual work principle, the deformed configuration, is transformed to the time t configuration. Therefore we say this is after the transformation. So we have the variable in the current configuration. We have transformed those into the current configuration. So therefore we expressed in the updated Lagrange format. And those are the variables. Those are the Kirchhoff stress and the green string tensor at t plus delta t configuration. Okay, and then we have transformed all them into the time t configuration. These are the time t configuration. Okay. Then we have the process of linearization of the equilibrium equation. Okay, and the virtual displacement formulation are nonlinear, and therefore the linearize this equation is first, and then to solve them. So similarly, for the non-linearization of the relationship, we have two formats: the total Lagrange format and the updated Lagrange format. The difference is we take the different configuration as the reference. Okay, as the reference. Some discussion point here. First, the relationship only apply to the linear elastic material. Okay, and for the the elastic plastic material, the linear relationship applied to link stress and strain rate. Okay, and for other material, which means rather than the linear elastic material, when the increment is small enough, the above relationship can be applied, and when the increment is a finite value, the relation is approximate value. Iteration method is usually applied to update the stress. The linearization of the formulation, we have the total Lagrange format. Okay, so this is the linearization method. We move the nonlinear item to the right as the virtual work. Use the iteration method to treat it together with other loads. When the time step is small enough, it's okay to ignore the nonlinear term. So we have the linearization equation in the two kind of formats. Okay, so part 2, we just really very quickly have gone through those. These are many mathematical equations, and it's not very important. So, but if you are interested in, you can read relevant books. So then part 3, F equations of geometry problems and its solutions. We have mentioned F equations before. Let's have a look how do we apply to the geometry nonlinear problems. So we have all those equations. For the static problems, so we have the point coordinate within the element can be expressed in the interpolate. Okay, so we have this is our coordinates. This is the coordinates at the current configuration. This is the coordinate at t plus delta t configuration, and we express as interpolation formats. Therefore, those are the coordinates at the nodes, and this is the interpolation function. The shift function is the interpolation function. And the displacement also expressed in the interpolation format. So this is the displacement, and then this is the displacement at the node, and this is the shift function or the interpolation function. Then we have the total Lagrange format equation, okay, which means we take the initial configuration as the reference, say, therefore these are the zeros, we use initial, okay, and then this is our stiffness equation for the geometry nonlinear problems. So we are very familiar with this equation for the general small deformation case. This is the corresponding equation for the large deformation case, and here we define different variables. We give the definition for different variables here, and so in those ones we have include the nonlinear items. So we are here, this KL1 is the element stiffness matrix in the small deformation case. So, and then we have some case for the geometry nonlinear problems. Okay, so here is the stiffness due to the initial displacement, called the initial displacement matrix. Then we also can express the stiffness equation in the updated Lagrange format. So we have using the current configuration as the reference, you see here, and then we have the stiffness matrix and the external force. And here we have the B is the stress strain matrix corresponding to the linear and nonlinear strain, and D is the material constitutive matrix. This is same as the linear elastic case, and tau is the Cauchy stress tensor. And then this is for the static case, and for the dynamic case we have to introduce the acceleration. Okay, we have to introduce the acceleration, and also again, so for the geometry nonlinear problem, therefore we have two kind of format. First, the total Lagrange format, and we take the initial configuration as the reference, and this is the equilibrium equation. Okay, this is the equilibrium equation for the geometry nonlinear problems using the update Lagrange format. So we use the current reference, current configuration as the reference. Okay. Then we just quickly go through the method for solving the F equations. So the basic idea is at each time point, or we can also call it increment step, we use the nonlinear equation solving method to obtain the solution through iteration. So the commonly used iteration method is the direct iteration or Newton-Raphson method we have mentioned in the nonlinear chapters. And there are two level iterations when solve the geometry nonlinear problems. First iteration is the increment, so we loop through the time or the loading increment step. The second level iteration is to solve the nonlinear equation derived from the time increment step, obtain the corresponding unknown through the iterations. There's two levels of iteration. Then we have introduce the method to solve the FE equations. First, the static problems. So we have this is our stiffness equation in the total Lagrange format, and then we have the stiffness equation in the update Lagrange format. Okay, and then for the dynamic case, we have the equation in the total Lagrange format and the updated Lagrange format, and we use the explicit integration. If you still remember the explicit algorithm, what is the explicit algorithm? For the explicit algorithm, which means the variable at time plus delta t can be directly solved or worked out from the previous variables, the variable at the previous time point. Therefore, you see in the right hand of the equation, all the variables are the variable in the previous time point. Okay, same as here. We are using the explicit integration. Therefore, those can be solved using the values at the previous time configurations. And for this method, there's no need to form the nonlinear stiffness matrix in each increment, and there's no need to iterate in each increment. Those are the advantages. Then we have the implicit. Integration. So for the implicit, so you see those in the right hand of the equation. You see those variables, and this is a dynamic problem. Therefore, we have the acceleration in the equations, and for the implicit integration, there's need. So we have to form the nonlinear stiffness matrix, and we have to iterate in each increment because those variables we cannot directly solve. So we have to, for those nonlinear equations, we have to do the iteration in order to solve this. So we can say for the dynamic problems, for the integration, the explicit integration is more efficient than the implicit integration. But sometimes for the explicit integration, you will get the error answers and the problems. So then let's do a quick summary of the difference between the total and the update Lagrange format. So the first difference, the reference configuration is different. Second, the total Lagrange method contains the initial displacement matrix, and the update Lagrange method only uses the current displacement matrix. And in the total Lagrange method, the stress and the node force are derived from the Kirchhoff stress. And in the updated method, the Cauchy stress is used, and therefore we need the transformation through the Kirchhoff stress. And in the total Lagrange method, the coordinate transformation matrix keeps the same, but in the updated Lagrange method, coordinate transformation needed to be updated, and in the updated Lagrange format is more applicable to the non-elastic large string problems. So this tells you in which scenario you should use the updated Lagrange format. So for the non-elastic large string problems, it's better to use the updated Lagrange format. So from this slide, we see there's many difference between these two different formats, and they both have advantage and disadvantages, and one format is more suitable to some specific scenarios, and the other format maybe is more suitable to other scenarios. So you have to, in the analysis, in the RP simulations, you have to, it's up to you to decide which one to use, and you should choose the correct one based on your knowledge. Therefore, you have to know all those theories, otherwise you don't know how to make the choice. Okay, so, and then finally, let's very quickly go through the constitutive relationship of the geometry nonlinear problems. So this is, and constitutive relationship, which means is the stress and strain relationship. So we said for the geometry nonlinear problem, we have two scenarios. First, the large displacement, large rotation, but small strain. Okay, so in case of small strain, the second polar Kirchhoff stress tensor and the green strain tensor, okay, do not change as the object translate and rotate. Their value equal to the engineer strain and the engineer strain, engineer stress and engineer strain, because there is a small strain. Okay, and in the first scenario is the elastic case. In the elastic case, where D is the elastic constitutive tensor, independent of stress and strain, and it is the elastic constant in this case. Okay, so for the elastic case, we have the elastic constitutive tensor expressed as this, and this is the corresponding constitutive relationship. And then the second is the non-elastic case, and for the small strain scenario. So in case of a non-elastic case, we use the increment to describe the constitutive relationship. Okay, so therefore we see the D, the symbol of D. So we use we have to use the increment to describe the constitutive relationship. So where ds and d epsilon are the differential of the Cauchy-Hopf stress tensor and the differential of the Green string tensor, and the big D is the constitutive tensor at current configuration, and we use the initial configuration as the reference. Therefore, we say the subscript is 0 because we are using the initial configuration as the reference, and it is the big D, the constitutive tensor is a function of Cauchy-Hopf stress tensor and the Green string tensor. Then we have the second scenario. The second scenario is we have large displacement, large rotation, and large strain. And the first case is the elastic case. The elastic case is the example is hyperelastic or hyperplastic material such as rubber. So for this kind of material, strain energy density is a function of the Green string tensor, can be expressed as strain variant. So for the rubber, a very typical model is the Monin-Rivlin model. So we use the strain invariant. Those are the strain invariant to express the strain energy density. Okay, to express the strain energy density. Those are the definition for the first invariant. This is the definition for the second invariant. This is the definition for the third invariant. And then here we can work out the second Cauchy-Hopf stress from the strain energy density. Okay, from the strain energy density, and then we can work out the constitutive relationship for the rubber. Okay, this is elastic case. And then we have another case is non-elastic case. So in case of large strain, the second polar Hodge stress tensor and the Green string tensor do not equal the engineer stress and engineer strain, therefore cannot be used, and the following equation is used instead. So we have the following equation. So for the for the non-elastic case, we have to use the stress rate and the strain rate to describe the constitutive relationship. Okay, and similar to the small deformation, we can work out other formulation and use the Cauchy stress, engineer strain instead. Okay, so this is a quick go through of the constitutive relationship for the large geometry nonlinear problems. We can see for different scenarios, for different cases, we have very different formulations, and the problem becomes very complex. Okay, and we here in this lecture we have just quickly gone through all this, but you need to read more and more materials in order to have a deep understanding, and in order to correctly use those theories. And I hope in the future you will be a good expert of those. Okay, that's all for this chapter. Thank you. I'll see you next time.